Hello, I'm Kenneth Baker, Chief Engineer with the Wireless Bureau at the FCC. We wanted to provide you with a brief introduction to wireless systems and spectrum. In particular, we hope to give you some comparisons between spectrum in the 2.5 gigahertz bands and the 3.5 gigahertz frequency bands. Others from the FCC will explain some of the trade-offs and options regarding licensing and availability and how to obtain operational spectrum. My focus is simply to introduce the terminology and some of the physical differences between these spectrum bands. In this brief presentation, I will introduce some of the basic components of a broadband wireless network. I want to also define for you what spectrum is and why it is important. In short, radio spectrum is the fundamental building block of a frequency broadband network, or wireless broadband network. While we don't cover the details here, I think most folks are aware that if different wireless networks use the same spectrum for the same location, each system might interfere with the operation of the other. For this reason, spectrum is regulated and licensed so that each user can have a suitable operating environment. It is the role of the FCC to regulate spectrum for exactly this purpose. Let's begin by looking at a wireless system. This figure shows the general components that make up any wireless communication system. The wireless part, the wireless component, is the RF signal shown between the antennas. A single radio signal is like a continuous wave or a sinusoid, as shown by the wavy blue line between the antennas. This is one reason radio signals are also called radio waves. The information is most likely digital data for our purposes today. The transmitter imparts the information onto the radio wave at one end of the link, and the receiver recovers the information on the other end of the link. One important concept to note is that when information is placed on a radio signal, a large range of frequencies are required, not a single frequency as shown above. Generally, higher data rates, that is more bits per second, require a wider range of frequencies. Bandwidth. The range of radio frequencies used for transmission is referred to the bandwidth of the radio signal. I promise this slide has the only math in this presentation. The difference between the highest frequency used and the lowest frequency used is the bandwidth of the signal. Since there are a great number of these radio frequencies, we also refer to this as the radio spectrum used by the system. We will say more about the center frequency, that's F sub C, of the band in the next slide. Some terminology. Wireless broadband communication systems use a range of frequencies, but we usually refer only to the center frequency in the bandwidth since it's easier. To be clear about terms, the frequency is how often the signal goes through a cycle from a high to a low and back to a high. One cycle is equal to 1 hertz. Now, hertz is a unit of measure for frequency, and it's named after Heinrich Hertz, a German physicist who first conclusively proved the existence of radio waves in about 1880. So, specifically, a hertz is 1 cycle per second. The frequencies that are useful for radio are a very large number of cycles per second. When we refer to 2.5 gigahertz and 3.5 gigahertz, we are talking about center frequencies that are approximately 2.5 billion cycles per second and 3.5 billion cycles per second. Radio waves also have an associated power. Radio licenses usually specify a maximum allowed transmit power. Being mindful of the legal limits for transmission is important when comparing spectrum options, since transmit power helps define coverage. In our diagram, power is proportional to the amplitude or the height of the sinusoidal wave. Spectrum considerations. So when comparing 2.5 gigahertz and 3.5 gigahertz spectrum, there are many considerations: cost, availability, types of licenses, etc., but also some of the physical characteristics which might make one band of spectrum more or less appropriate for a particular system. Example physical characteristics are shown in this slide. In general, lower frequency spectrum has better coverage characteristics than higher frequency spectrum. That is, lower frequencies tend to travel further for the same amount of transmit power. Better coverage implies that you need less transmission equipment and thus reduces the expenses of providing service to a given location. Lower frequencies tend to penetrate trees and into buildings better than higher frequencies. At the same time, more usable bandwidth tends to be available at higher frequency bands. So while these general statements are true, it should be noted that both 2.5 gigahertz and 3.5 gigahertz are close enough to each other that the physical differences will be small, but perhaps noticeable. It is well worth performing a comparison to see differences in cost and performance between 2.5 gigahertz and 3.5 gigahertz systems for your particular needs. Broadband networking basics. Well, broadband networking can become complicated partly because there are many equipment and technology options available to complete a network and provide service. Some of the many options are shown in this slide. Notice that a broadband network can include both wired, usually fiber optic cables, as well as wireless components. The 2.5 gigahertz and 3.5 gigahertz are suitable for wireless distribution and backhaul, as well as distribution directly to the end user premises. The end user could be mobile, and a mobile user is not shown in this figure. The best option for backhaul and distribution depends on several factors, including terrain, population density, service requirements, and the available budget. There will be many trade-offs to be considered. For example, fiber has lots of capacity, but it is expensive to deploy. This can be particularly true in rural areas. In these situations, fixed wireless may be the most cost-effective. Comparison of 2.5 and 3.5 gigahertz. This chart tries to capture some of the major considerations between 2.5 gigahertz and 3.5 gigahertz spectrum. Note that the specifics of licensing types will be discussed by others from the FCC, but I list them here since the availability of licensing and the costs associated with licensing will play a significant role in the planning process. Also, the amount of bandwidth available, which is largely defined by the licensing type, will drive the capacity and the throughput in terms of bits per second that can be achieved with a given network. Finally, there is the cost and availability of equipment to be considered. The 2.5 gigahertz band has been in use by educational institutions and some commercial wireless entities for some time now. As a result, equipment manufacturers have equipment readily available on the market. The use of 3.5 gigahertz for broadband connectivity is relatively new but growing fast. Equipment is available today, but perhaps not yet at the price point and level of availability of 2.5 gigahertz equipment. That is all I had for today. Thank you for your time. Please reach out if you have questions or need help in some way. If you have questions specifically about the rural tribal window, please email ruraltribalwindow@fcc.gov as shown in the slide. Our website, www.fcc.gov, has a wealth of information. My email is shown also in the slide if I can be of assistance. Thank you for your time and attention today.